A high-performance, fully concurrent garbage collector, and yesterday, JIT, concurrency, and garbage collection. So I'm going to be talking about particularly two of those, concurrency and garbage collection. Now, building virtual machines is hard, so anyone who likes building virtual machines must like pain. If you want to do garbage collection as well, you really like pain, because as Steve said, if you make a mistake, maybe you get something wrong with your GC map, so you don't know which slots on the stack actually are references. Typically, you don't find out that you've screwed up until many millions of instructions later, and debugging is really hard. And that's even for the simplest stop-the-world single-threaded collector. So that wasn't painful enough for us. So we decided to build a concurrenter that has multiple garbage collector threads. Obviously, there are multiple user threads. The garbage collector and the user program is running at the same time. That's what we mean by concurrent. If that's not hard enough, we have written a collector that moves objects in order to get rid of this fragmentation problem that people were talking about earlier. So you've got to be very careful about that your references to objects are up to date because you're moving them. And then to make it really painful, we're going to do this in a fully concurrent way. So there is never a period when all of the user threads are stopped. We only ever stop one user thread at a time. So there's all sorts of opportunities for things going wrong. And the question is, what can you do about this? And how can you set about building these things with some kind of confidence that it's going to be correct? Now, maybe the ideal way to do it is to take the approach that Steve's done with Mu, which is to produce a formally verified micro-virtual machine. But that's an awful lot of work. And so we've taken an approach that's somewhat more straightforward, certainly quicker, and something that we think is sufficiently easy to get to grasp with that reasonable programmers can do, and to do with some assurance. So I'm going to talk about a particular collector, but really what this is all about is lessons in how to build this kind of complicated, fully concurrent system and do it with some kind of assurance that what you've done at the end is going to be correct and to be high performant. So, who's done work in garbage collection? A few, right. So most of you haven't. So I'm going to make no assumptions. I apologize to those who know lots about GC if I'm teaching them things they learnt in kindergarten. So I'm going to give a broad overview of some GC algorithms. I'm going to talk about our case study, which is this on-the-fly replicating collector, and I'll explain what those terms mean. It's called Sapphire. And then our approach. We talked about abstractions and invariants. Abstractions and invariants really are our friend. It's too difficult to talk about, to reason about what's happening at a kind of a micro level. But if you think in terms of abstractions and make sure that the actions of your user program, the actions of your collector maintain those invariants, then you can be confident it's right. And then something that's quite interesting, I'll talk about how we can improve copying speed with using transactional memory. And to disagree with Francesco, I found model checking very useful. And I don't have to unwind loops infinitely many times. My model checking terminates without that. And we used this when we got into difficulty. And we used it by a colleague who's working on this. We hadn't got any experience with model checking before. Literally, he took a model checker home overnight, came back the next morning, found our bug and fixed it. So. But you are not a professional programmer. Sorry? You are not a professional programmer. No. I'm talking people that have no formal background. Okay, well, see you, and then we'll discuss. Right. So, yeah. Oh, I'm not real. I'm just a chimera. Right. Okay. So, to build this thing, I have to say, it was extraordinarily difficult. It took a long time, and it was built by some really clever people, which are not me. They're my colleagues, Carl Ritson and Tomoharu Ogawa from Kochi University in Japan. They did the real work. I just gave them my opinions and said, do this, don't do that. So, a little bit of background. I'm just going to talk about tracing collectors. I'm not going to talk about reference counting. There are two broad kinds of tracing collector. The idea is that you have some set of roots, which might be, which I've indicated here, things like your thread stacks, global variables, so on and so forth. You start from there, and what the mark sweep algorithm does, it finds an object. It says, oh, okay, I've got an object here. I see that it's got a couple of children. I'll put those on my to-do list, which might be a stack. And then I'll carry on, and hopefully I will have if I've done it correctly, I will have traced the whole graph. And as I trace each one, maybe I'll put a mark in it. I'll indicate that it's marked and I've seen it somehow. And at the end of this, I should have visited all of these objects except for C. And so C is garbage and I can reclaim it. So my second phase of this, I will sweep through the heap, probably linearly. I will discover that C is marked and I will reclaim it. And I will do something to reset the marks on everything else. So that works very nicely. It's simple because we're not moving anything, so there's no problem with having to change the value of these addresses on the stack that are pointing to my roots. You can see I've colored things, and I'm going to talk about abstractions as I go, but the idea here is that we've seen at this point, the garbage collector has discovered this object, and it knows what its children are. So conceptually, we've colored it black to mean I know about this object, I know its children, I don't need to go and visit it again. But these other two, which I've colored gray, the intuition is, I know they exist, but I know nothing else about them. I haven't gone and looked into them. I haven't seen what child pointers they have or so on. And so these gray objects are, if you like, they're our work list, and I probably usually implement the work list by having a stack and push and pop things on stacks. That's in the simplest sort of collector with only one thread. So that's mark sweep. Another way to do garbage collection is by copying. Now the problem with the mark sweep collection, as you've seen, I'm not moving anything. So if I end up with holes in the heap that aren't big enough to fill any allocation request, I've got fragmentation and I've got a problem. And any collector that doesn't defragment, if it's working with a long-running program, that program is going to crash, because real programs tend to suffer from fragmentation and break. So I'm going to talk next about copying garbage collection, and the example I'm going to show is due to Cheney, and I think I've got a date that's even older than the ones that I've seen before, so an old paper, but it's kind of cute. So here's how it works. So here we have a data structure, and I've divided the heap into two parts, one of which is called from space and one of which is called to space. So all of my objects at the moment, they're all sitting in from space, and here's a pointer from some roots or something. One of the interesting things to note here is that we've got some sharing. That object is reachable from more than one place. So what we do in a copying collector is we start by copying the first object we find into to space. So we've copied this object L. It's still got its pointers to the objects in from space. And we've got a couple of, if you like, a couple of fingers, one called scan and one called free. Free is where we can allocate the next thing we copy. Scan is where we've got to in examining what we've done. The other thing that's important is I need to leave behind in my old object a forwarding pointer saying where I've moved it to. This is important for sharing, because a good example of why that's important, suppose you've got a cycle of objects. As you copy them, you really don't want to unroll that cycle into an infinite sequence of objects when you only had 3 or 4 to start with. So you need to be able to preserve the topology, and that's what that pointer is for. So, first thing we do, we look at what the scan pointer is pointing at. We find there's an object. It's got a couple of children. They're pointing to A and E. So we copy those. And as we copy them, we update the pointers in this 2-space object to refer to the new copies. We update the free pointer to where the next place we can allocate is. We update the scan pointer. So implicitly, anything before the scan pointer is black. We finished with it. Anything between the scan and the free pointer is our work list. It's grey. Does that make sense? And we carry on like that. So now we scan A. We see what it is pointing to B. So we copy that, and so on, and so on. And eventually, when we scan D, our scan pointer is pointing to our free pointer. So we finished. Nothing else is grey. So how do we know when there's no work left to do? There are no grey objects. And we're done. Is it correct? Have we preserved the topology? Yes, we have, because we saw that when we copied we see we've got the pointers all pointing in the right direction, and we use the forwarding addresses to make sure that happened. Okay. So the heart of this, this is a simple two simple stop the world collectors, and I was talking about objects being black, white, or grey. Now, this helps a bit when you're doing simple collection, but it really, for simple stop-the-world collectors, you can figure out most of that in your head. It's kind of obvious. When you're doing things with concurrent collectors, it gets much more tricky, and that's where these abstractions come in really handy. So this is a Tricolour abstraction. It's very old. It's due to Dijkstra in, about 1978, and he's proposed that we think of objects in terms of 3 colours. The first one are ones that have not yet been reached by the collector. The second one is ones that have been visited by the collector. These are the grey objects, but their fields need to be scanned. And once we start talking about concurrent collectors, we see that objects may revert from one colour to another colour because there's been some action taken place by the user program, which has changed the shape of the graph, and maybe we need to look at these things again. Black objects, on the other hand, have been visited by the collector. All their fields have been scanned, and we know that we're finished with them. So when we finish doing a garbage collection, what can we say about colours of objects in the heap? There are no grey objects left. Yeah? And so the objects we want to preserve are all black, and anything that's white is garbage, and we can reclaim it. Okay? So it's a quite simple, straightforward abstraction, but it's remarkably powerful. And we'll see later how we can extend that power. So a bit of terminology. If you read old literature on garbage collection, it's quite loose with the way it describes things, whether it describes things as parallel or concurrent or incremental. But I think it's useful to have a standard definition. Most people adopt this one. So here, these little pictures are meant to indicate each stripe, if you like, is a thread. So here we have 3 mutators threads and maybe 1 garbage collector thread, and time is running from left to right. So the simplest kind of collector is a stop-the-world collector. That means you run the program, your heap becomes full, and you make everything stop. And you do a garbage collection, and when you're finished, you start everything up again. And this was the sort of behavior that used to give garbage collectors a very bad reputation for being really, really slow. Though there's an apocryphal tale of an Emacs implementation when they changed the message that Emacs was garbage collecting to Emacs was waiting for NSF traffic, and asked users if they thought it had speeded it up. And the user said, yes, it's going much better now. So here we have stop the world, mutators run, everything stops, we do a garbage collection, start up again, we run again, fill the heap again, stop, and do another one. So that's obviously not very efficient, doesn't make good use of processor resources if you've got a multi-core processor. So we can make it parallel. Instead of having 1 GC thread, let's have lots of GC threads, and that should shorten the time it takes to do the collection. But it still stopped the world, so you've still got these big pauses. Another way to do it is incremental collection, whereby we have the user program, which we call the mutator. We call it the mutator because, as far as we're concerned, all the user program is some kind of irritation that just changes the shape of our heap while we're trying to run. It just mutates the heap. Generally, we're not really cared what values it writes. So here, we have the user program do a little bit of work on behalf of the garbage collector every so often. And the idea is that this is going to reduce these garbage collection pauses. Typically, there's a pause at the beginning to start everything off, and there might be a pause at the end to finish everything. But for the most time, the garbage collector and the mutator run in this kind of interleaved fashion. A common way to do it these days is to do what's called mostly concurrent GC. So it's called mostly concurrent because most of the time we've got the user threads running in parallel or concurrently with the garbage collector thread. The reason it's called mostly concurrent is because, again, there's usually some brief period when we have to stop the world, get everything ready for a garbage collection, and similarly stop the world at the end and finish. The sorts of things we have to do when we stop the world maybe stop all the threads and scan their stacks to find out what their roots are, where they're pointing at objects in the heap. The sorts of things we might have to do at the end, particularly if we've got a Java implementation, is deal with reference types, which are tricky, or deal with finalization or something like that. That's the kind of thing we need to do. So let's go make all this as concurrent as we can, and a fully concurrent or on-the-fly collector runs like this. You've got the mutator threads running almost continually. You might stop one thread at a time just to scan its stack, but you're never stopping all of the threads at the same time, and the GC is running concurrently with the mutator threads, and you might have more than one GC thread as well. Any questions about that? Does that make sense? So this is what we're trying to do. We're trying to do this one. Right, so let's talk about Sapphire. Sapphire is an algorithm originally developed by Elliot Moss and Rick Hudson. It's an on-the-fly concurrent replicating GC. So on-the-fly means it never stops more than one thread at a time. Replicating means that it's a copying collector. It's trying to build two replicas of the heap. And when it's finished building the replica, it will switch over to using that rather than the original one. And this gives us, defragments a heap. It uses copying. One of the advantages of having a defragmented heap is copying is very fast. Essentially, you just have a pointer to the next part of free space in the heap, and you just increment it by the size of the allocation you want to make. So it's very fast. And we eliminate fragmentation. If you've got mutator threads running at the same time as collector threads, you've got a problem of synchronization. You've got to make sure that both the mutator threads and the GC threads have a coherent and consistent view of the heap, or at least eventually. And the question is, who pays for that synchronization cost? Should it be the user program? Should it be the collector? Should it be a bit of both? In general, you don't want to make the user program pay because that slows everything down, and it slows it down a lot. So the way Sapphire works is that the GC pays most of the cost of synchronization. So we built a new implementation of this in JIKES. We added a number of novel features. We did it in JIKES RVM, which is Java in Java virtual machine. And you get all the benefits of having a type-safe language for implementing your virtual machine and your collector. Although obviously there are a few bits right at the bottom which use plain C. JIKES RVM has been hugely useful to people doing this kind of virtual machine research because it's designed for research. It's designed to be easy to replace components. And it's great credit to the people behind that they built that system for the rest of us. So here's how Sapphire works. Sapphire operates in a number of phases. And it's as I said, it's a replicating collector. Essentially, it's a copying collector. It's got this notion of from space and to space. So initially, the mutators are running along quite happily. They're reading and writing data that's sitting in from space. And objects in from space, they have a header, and they have some. So that's how we work normally. The first thing we have to do is we have to do marking. And the way that Sapphire marks objects is it traces all the objects, live objects in from space, and for each live object, it creates an empty shell in to space. Apart from that, the shell is empty. It doesn't copy the data. All the objects that are live, and now we point in the used everything is replicated properly and any up. If the garbage collector wants to copy data, from reading and writing to as a black object, by which I mean when we finished, we throw yes. We have time, so you've got these phase changes are very yes, yes. So we have a what you're doing. So if it's a generational collector, it will worst possible situation. And this is the thing. Objects and colors, and this Tricolour abstraction. This is a sort of a thought experiment. What could make our collector incorrect? To hide an object that's reachable, i.e. that's live, that's reachable from starting from your stacks or from the collector, so that the collector a bunch of objects like this. Mark it black. These two would be grey. And the Mutator program comes along and says, that. And now the collector wakes up and it says, objects left. No, am I? Lost object problems. So maybe Mutator comes along, visits this object. Oh, I'll write a pointer from here to here, and and we color it black. How are we going to solve this? And the answer is we use and to make that collection strategy yeah.
When you move a child
Just in terms of the colors there.
yes.
That's one example. You've got a pointer from a black object to a white object. And the you're only going to that's the first condition. And secondly, white object have been destroyed. Follow the pointers and trace through the pointers. So, if you want us, because we to prevent one or other of these invariants from and different strategies observation. The first invariant the second you must make sure that there's a condition from arising. The answer is a little piece of code that we insert when put field bytecode is what you modify to do that. And effectively, anything that was live then continues to be live. Shock barrier, it might save an object from being colors of mutators, and there's really quite elegant. And to be rescanned, it means old references at the end of the or white references. The other kind references they will never if you're enforcing you make it black before you load it. Or to point, sorry, I forgot to. So what does that say to us about the so we don't want any black to white pointers. Reverses the that are not reachable, not this. And then I know I'll find. If I'm unlucky, What does that say about the mutator? Are the actions of the collector is and then we have to look at each thread. And if we have ended up shading any, then we've got to finish, and we scan the threads. Okay, I'm not going to do this concurrently anymore. With a black mutator, it means that once the so the deletion to termination is much with initialisation, because trying to use a deletion barrier straight black here, and then maybe deletion barrier we start off with an insertion barrier. We can let some of them be grey, and then so what I hope you got so far is this idea of these are think not only in terms of colours of objects, but also let's move on talking about Sapphire a bit. We're going to stop every user thread where these running in another phase. We have these kind of ragged phases. You run the mutators, and they're are observing the GC in one state. For a little are mostly concurrent. All the mutators are the same at some point. we have they've all recognized at the same time. No. That the GC state has moved on, they might be running simpler to do than others. That has happened, and collector threads are running to the state. To do if I'm allocating them black, and these we switch on a barrier. So we mutators running with a barrier. There are two kinds of while we're trying to copy a field, the mutator collector wakes up again and writes the old field back to Now compare and swap is quite expensive. Other one. Uh, um, who knows who's looked at transactions? Take a Intel's transactional support does this. Code, you say X begin, you do what you want, and then we finish. Committed. If another thread has done something, particularly by leveraging the cache coherence, and kilobytes of reads and writes. So however, it's not a transaction for every individual. A compare and swap is on modern. Want to do fallback too often. So that when we typically what you do, you'd load space location into and if it aborts, you go and try it again. If the mutator has so that's using compare. We could do it like that, but that's not a good idea. With plain simple load, plain simple store. Load our first field, we'll store it, we'll load our second field. CAD stuff works nicely. Copying. So we're collected but kept together by because I'm putting all these things into this. Yes, that's one problem, yes. Yeah, okay, you're on the find out what its type was. We might need to find out action. And there's a problem issue, you know. Well, what we'll do first of all is we'll planning all these objects first, finding out everything we need. Essentially, read the field, write the field. Well, it only works on Intel processors which have hardware transactional extensions. So I thought, I wonder if we can do it in software. Memory. It's not a complete software transactional memory. So we do the transactions that you saw. Actions, and then we verify the verification. Why do you think we have to put a fence? so we have to put a fence in. Fences are moderately expensive, but hey, we've done a lot of work before we have to put that fence in. And so it works, and it works quite nicely. The question is, how fast does it go? So I haven't got many slides on performance, but here we have comparing for a bunch of da capo benchmarks our performance, either using the old collector copies every field using compare and swap, or using hardware transactions, or we're using these hardware transactions where we put lots together, or by using software transactions. And if you look at here, the black lines are using compare and swap. Taller bars are better, and you can see we get performance that's pretty much similar using software transactions as we got with using hardware transactions.
Why is that? I would expect hardware would be faster. Right?
You would, wouldn't you?
Yeah, so why is that?
So the reason why that is, and it's also the reason why this isn't a general transactional mechanism. So what hardware transactions, they commit these transactions, and they guarantee that they've done some transaction, and it's visible to everybody now. What we can get away, so every mutator's view is consistent. Because these transactions, either they happen instantaneously or they haven't happened. Yeah, we can look at it like that. The reason our software transactional memory works efficiently is we don't need that immediate guarantee of consistency. We can afford to have a much more relaxed view of consistency. All we care is that once we've come to change state, say from finish copying to finish copying and we're starting to flip, we only care that everything is consistent at that point. So we can afford to be relaxed. You couldn't afford to be relaxed, you couldn't do what I've just showed you if you were trying to build a general purpose software transaction system.
Right, so if you had done that, it would have been much slower.
It would have been much slower, yeah. But we can afford to be relaxed. We kind of say, we don't care how far you've got, as long as when you've finished, all the writes are visible and have been done. Yeah? Right. It's certainly the case that when we turn on the collector and we start doing this, it does slow the system down. Yeah. But we try to run for as much time as possible. We've done a number of experiments. What should our policy be about running the collector? Should we run it all the time to try and to get the smallest heap, or should we give some headroom in the heap and allow the system run with no collector, then turn the collector on and collect? And the collector undoubtedly slows it down. It doesn't slow us down as much as other real-time collectors slow down.
My question is about the actual, so when you show your transaction, these are fast as slow as you cast. And I was just wondering how often...
how often do the transactions abort?
Yeah, pretty much.
Yeah, very rarely.
Okay.
Hardly ever. I would have to look in a paper we wrote in ISMM a couple of years ago to tell you the number. But if you'll accept my sort of hand waving, hardly ever. It is hardly ever. Yeah.
Implicitly shows through the data, right? If it happened a lot, we would be much closer to cast performance.
Yes. Yeah.
Worse than cast performance.
Yeah, exactly. You can kind of infer it from that, but I think we do actually have some hard numbers. Yeah. Yeah.
If it doesn't abort, does it mean that the mutator is not actually...
We have two options. We could try and do the transaction again. Or we could say we'll fall back to using compare and every time, we'll fall back to compare and swap. Any other questions? So, is it correct? Correct. Well, the first thing is it's correct. Assertions that really valid. If you've copied everything to 2-space, to do that, and so on. There's lots of non-determinism in terms of how in JAX RVM, and if I run them correct, is it to say the system is correct? Came across a and the problem we found in particular but what you do is you typically object, and at the same time a mutation. And then Tomoharu says I found out what I needed to change. So model checking, what is it? It's a very in every state. Language called Promula. You write that guarantee that our system is correct, but to give us as implement. An x86 relaxed memory process. So broadly, the memory process, it has the CPU add stores to a local FIFO store buffer. We've got store load forwarding, so any core can see any store in its own buffer, but not others. And only the core that issued a write can read the latest value. And we assume cache coherency. And the code is really very simple. This is kind of exactly the code. I say kind of because I should put backslashes on the end of every line, but I can't be bothered to do that because it looks ugly. So here's our mutator, and it writes a value AV onto this channel, mutator queue channel. It stores that value locally. It increments the counter on that channel. Here's a read. It says, it looks at the count there. It reads that from the shared memory. Otherwise, it reads. So if there's nothing in the queue, it reads it from shared memory. That means the store buffer is empty. Otherwise, it reads it from its local store buffer. So it's pretty simple. I mean, here's, we can do commits. We can say, we can commit the value into shared memory and decrement the count. Here's how our memory works. We have what this syntax in Promula means is it says non-deterministically choose one of these actions, do it, and then go around and do it, and loop around doing this endlessly. So non-deterministically, we choose whether to commit a write-up from the mutator queue or whether to commit a write from the collector queue. So it's infinitely repeated non-determinate choice, which channel to drain. Here's our scenario. It's a very simple one. You can tell me this is not an industrial scale because I have one object. So we have one object and it has one field. I said it's a non-reference field. It really doesn't make a difference whether it's a reference field or not. Here's what the mutator does. It keeps on changing the value of a field. So here we keep on flipping the value of this field x. We write to from space, we write to to space. If we've gone through the flip space, if it's not flipped, we read from space. If it is flipped, we read from to space. And what we want to check is that the mutator reads what it wrote. If the value that the mutator reads is the same as the last value it wrote, we're correct. If it doesn't, because we've got some kind of bug with this double writing and the flipping and so on, it doesn't. And that's what we chose to do. So, oh yes, here's the collector. The collector reads from space, reads from to space. If the values are the same, we break. Otherwise, we do compare and swap. So this is our implementation of compare and swap. We've got a fence in it. When we finish doing that, this is the fence at the end of our phase. Now we've changed phase. So we can implement it for CAS, and that's all the code it takes. Or we can do it for our software transactional memory, and again, it's the same kind of thing. And that's all the code it took to do. It's the sort of thing that I think a programmer could get familiar with once they've learned the Promula language. It's not terribly complicated. We used it for a number of things. We used it for this problem of hash codes that I just mentioned. That, you know, if we've got some data and it's hashed, the hash is maybe the address, and when we move it, we need to remember what that hash code was. And we used it for doing that. Through that. So that's just a state transition diagram of moving from hashed, unhashed to hashed, hashed and copied, and so on. I'll flip on to that. Any questions about that? Other things that were tricky? I'm running out of time, so Java reference types. Java reference types are particularly horrible. There are all sorts of weak reference types. Soft, weak, phantom. Go look in the online documentation for Java reference types. The only place it's documented is in effectively the Java doc for those. It's not defined formally. It's hard to understand in some ways, and it has a number of. Oops, sorry, what did I do there? Press the wrong button. It has a number of unpleasant consequences. So basically, the idea is you have a reference object, maybe a weak reference, and it points to some normal object. It has to point to some normal object, and the collector, at its discretion, can choose to reclaim those objects and null out these pointers. The reason it does that is it's useful for building caches and things like that. The rules are that if the collectors decided to reclaim that, this reference better be null, because you don't want a reference to something that's being collected. What reference get does is it will return you a strong reference to that object. So effectively, by calling get, you might make an object that was safe to reclaim, unsafe to reclaim. Because before it was only reachable by a weak reference of some sort, and now it's reachable by a strong reference. And if you're trying to do termination of your GC cycle, and you're trying to do that on the fly without stopping the world, you've got a problem, because really you need to make sure that all the references to this object become null at the same time. And there might be many of them. It's particularly nasty if you have something like this. So here's an object that has a weak reference to this object, and another weak reference which eventually reach that object. If you decide you're going to reclaim this object because of memory pressure, you've got to null out that, and you've got to null out that, and you've got to do it atomically as far as the Mutator program is concerned. They've all got to go to null like that. Now, if you're trying to do things concurrently without stopping the world, that's difficult to do that. So, what did we do? Oh, you don't want to read the specification. Is this important? Yes, there are a lot of reference types in typical benchmarks. What can you do to deal with reference types? Well, you could stop the world. We don't want to do that. We could block any mutator that calls get. So if at the point you're trying to terminate, a mutator calls get, you say you're blocked until we finish processing all these reference types. Or you could process them all on the fly, never blocking a mutator other to scan its roots. And we ended up writing a sort of state transition where we start we're running normally, we start tracing, so we're in a tracing state. If we finished, we've got no tracing work left, we move to a state where we can do clearing. If any mutator calls get, we switch to a state where we've got to repeat and we start tracing again. And the aim is to switch atomically from tracing to clearing like that. You can do this using insertion barriers. Don't try to read this, or you can do, but the problem with an insertion barrier is there's no guarantee that it will terminate, because you might call get, and then you've got to go around, you've got more work to do. You can use it using deletion barriers, and in this case we get termination guaranteed. Now, how do I know that this one is guaranteed and not the other? You could take my word for it, which would clearly be a good thing to do. But if you're of a deeply skeptical mind, which I hope you are, you could say, I want something better than that. And the answer is what we did was we used model checking again to check those two pieces of code. And indeed, lo and behold, it demonstrated that if we used the deletion barrier, we got termination, and otherwise we didn't. One thing that was really interesting is we measured execution times. So there are three things you can do. I think the first thing you could do is you could have this, you could say, well, if you try to call, you can stop the world while you process all the reference types. The second thing you could do is you could say, well, I'm going to use a big fat lock to make sure that we process these. You know, when we try to deal with reference types, they're locked, so mutated. Or you could do it on the fly. And it turns out that actually doing it on the fly, with all the overheads of on-the-fly collection, turns out to be faster. Why does it turn out to be faster? Because it means that while we're trying to process our reference types, other mutators can carry on running the program and so on, and we don't have to actually stop the world. So this was a surprise to us. We didn't expect it to be faster, but it turns out to be slightly faster in all cases. Yes, I said that. It works with deletion barrier without. We use model checking to do it. So my evaluation of model checking, it was something I was new to, but I found it to be practical. It's easy to construct and check these models. Doesn't give you a 100% guarantee of correctness, but it gives you a lot of confidence. And concurrent collectors are complex, and it's very easy to overlook corner cases. And model checking offers us a reasonable confidence in our algorithm at a reasonable cost. Punchline. It's useful to have a formal specification of these things. We had this model checked implementation. Our on-the-fly reference processing phases were longer in the worst case, but with deletion barriers by not by much. And overall execution time, though, is not increased and often reduced. So, summary. What I want you to take away from this, I guess, is that on-the-fly copying collection for a full Java virtual machine is very complex, but abstractions and invariants give you a handle on comprehending it. Model checking is a practical way to provide confidence in these algorithms. So, questions? That's it. And despite what I said about it being hard and painful, GC research is fun. Do it. Yeah.
So you didn't mention generation of large collection?
Our collector isn't generational. I don't see any reason in principle why it couldn't be made generational. It'll be a certain amount of engineering work because your barriers are having to cope both with the idea of generations and with the idea of concurrency. But I don't see in principle that it will be difficult. We did. We compared it with collectors that we thought were similar because we wanted to understand what was going on in the shape of it. So first of all, we compared it because we wanted free. So what we did is we had the implementation running with some heavyweight benchmarks like the Da Capo ones, and we also had another process which fired short-lived tasks, at it. These tasks were simply sort of things like manipulate a small tree or something like that. And we measured how long it took these tasks to execute. Because what we're looking for is the responsiveness. So normally your task should take, I don't know, so many milliseconds. How much does it take with the garbage collector running? So that's the kind of thing we did. And the answer is, it performs much better. I would say that, wouldn't I? Yeah, but it does, trust me. Yeah. Yep.
We saw there was one garbage collection thread that was collecting for multiple Mutator threads.
Yep.
Does this framework extend to multiple garbage collection threads?
Yes. Ours is, we have multiple garbage collection threads.
Okay.
Yeah. Yeah. We were running on an AMD machine with 64 cores, and we found we got best performance if we devoted about 8 cores to the collector.
Richard, there's a question.
Yep.
I was wondering, it seems from what you described, it seems really, really hard to figure out what the state of the heap is at some point in time. Like, how much free space do I have, or how much will I be able to reclaim, or when should I start collections of the view? Or is that not correct?
Well, the only way to determine how much free space you've got is to know how much space you've used. And the only way to know how much space you've used is to do a trace. So, I can't tell you how much free space there is until I've finished this marking phase. And then I know how much space I need.
But it seems to be even more complicated in this design than in other designs. So I was wondering, did you do anything special? Did you like come up with any good ways of determining when to start collecting, when to collect how the rest of it?
We talked about that for a long time. I mean, you could have the collector running continuously, but that slows everything down. I think what we did in the end, we had the collector run again after so many megabytes of allocation. So finish the collection cycle, wait so many megabytes of allocation, and then start collecting again. But there are lots of different ways, lots of other different heuristics you can use to do that. I mean, one other thing I didn't mention, we have a number of spaces. We have a separate space for large objects, so we don't copy those. We have a separate space for volatiles, so we only have one copy of a volatile, because we need that to get. It's the simplest way to handle volatiles. Yeah.
The collector needs to do a fancy to issue their mutators. And is it possible that the one of their mutators did not reply? Will the progress of the collector be guaranteed?
I think I would have to ask Tomoharu exactly what he did. There are two ways you could do that. One is to say, yes, you need to wait for it to reply. The other way to do it is that, well, if it's not replying, it's blocked. And I'll ensure that when it comes back from being blocked, it knows that its state has been changed. I think we did the latter, but I would have to ask him or look at the code, and it's a long time. Yeah.